Right now, underneath Yellowstone National Park, there is a reservoir of partially molten rock, roughly 60 kilometers long, 40 kilometers wide, and sitting about 8 kilometers below the surface. The last time this system produced a full-scale supereruption, roughly 640,000 years ago, it ejected over 1,000 cubic kilometers of material into the atmosphere. For context, the 1980 eruption of Mount St. Helens, the one that flattened 600 square kilometers of forest and killed 57 people, ejected about 1 cubic kilometer. Yellowstone did 1,000 times that. And it's not even the scariest thing on this list. It's number 4. We looked at planets that break physics. Now let's look at the things right here on Earth that are waiting to break everything else. This is a video about 5 real catastrophic scenarios. Not hypothetical, not science fiction. Each one has happened before. Each one has a non-zero probability of happening again. And for each one, the gap between what we know and what we're doing about it is, to put it gently, noticeable. We're ranking them from lowest immediate threat to highest. And by the end, one of these will have already started. Number 5. The La Palma Mega Tsunami Hypothesis. In 2001, a pair of researchers published a model suggesting that if the Cumbre Vieja volcano on the island of La Palma in the Canary Islands erupted and a massive chunk of the western flank collapsed into the Atlantic Ocean, the resulting landslide could generate a mega tsunami, waves reaching 30 meters or higher, that would cross the Atlantic and hit the eastern seaboard of the United States within roughly 8 hours. The paper got attention. The Discovery Channel made a documentary. The idea entered public consciousness. The problem is that subsequent research has significantly challenged the original model. Most volcanologists now consider a single catastrophic flank collapse unlikely. The failure would more probably occur in stages, producing smaller waves. A 2013 reassessment found that even in a worst-case partial collapse, tsunami heights on the U.S. coast would be closer to 2 to 3 meters than 30. Still dangerous, but not the civilization-ending wave from the original paper. La Palma is on this list, not because the mega tsunami is certain, but because it illustrates how we handle disaster science. We either panic or dismiss, and neither response involves preparation. The volcano erupted in 2021. The flank didn't collapse. The seismologists are still watching. Number 4. Yellowstone. The popular version of this story goes like this. Yellowstone erupts every 600,000 years. The last one was 640,000 years ago. Therefore, we're overdue. This is bad math. 3 eruptions separated by 2 intervals give you an average of 725,000 years, which means, if the average means anything, and the USGS is clear that it doesn't, we're roughly 90,000 years early, not late. More importantly, the USGS explicitly states that Yellowstone is not overdue, and that scientists are not convinced a supereruption will ever happen there again. A January 2025 study in Nature found that Yellowstone's magma is stored in 4 separate reservoirs, and only those in the northeastern region remain in contact with the deep mantle heat that could theoretically keep them eruptible over geological timescales. The western reservoirs are cooling. The system may be dying. But here's what makes Yellowstone interesting for this list. The threat isn't the supereruption. It's everything else Yellowstone can do. Hydrothermal explosions, blasts of steam, and superheated water are far more likely and can crater areas over a kilometer wide. Smaller lava flows, like the ones that last occurred roughly 70,000 years ago, are plausible, and none of these require the full system to wake up. Yellowstone doesn't need to be a supervolcano to be dangerous. It just needs to be a regular volcano in a national park visited by 4 million people a year. Number 3. The Cascadia Subduction Zone. This is a 1,000-kilometer fault running from Northern California to Vancouver Island, where the Juan de Fuca plate slides underneath the North American plate at roughly 4 centimeters per year. The last time it ruptured was January 26, 1700. We know the exact date because the resulting tsunami was recorded by coastal residents in Japan. The earthquake was estimated at magnitude 8.7 to 9.2. The geological record shows at least 19 major earthquakes on this fault in the past 10,000 years, with a recurrence interval averaging roughly 500 years. The southern portion of the zone is more active, with an average interval of about 240 years and a roughly 40% probability of a major earthquake in the next 50 years. For the full margin rupture, the magnitude 9.0 scenario in the USGS estimates a 10 to 15% probability within the same window. A February 2026 study from the University of Washington found that the fault may not be fully locked. The northern portion remains stuck, but the central region shows slow slip events and fluid movement that could influence how a rupture propagates. That's potentially good news. Fluid pathways might limit how far a rupture spreads, or it might mean the system is more complex than the models assume. Either way, when this fault breaks, the shaking will last 4 to 6 minutes. Portland, Seattle, and Vancouver will be in the zone. Oregon's projected economic losses alone exceed $32 billion. Essential services, water, power, hospitals could be offline for weeks to months. The last Cascadia earthquake was 326 years ago. The average recurrence interval is 500 years. The longest known gap in the past 6,000 years was 291 years. We've already passed that. Number 2, a Carrington-class solar storm. On September 1st, 1859, British astronomer Richard Carrington observed a massive white light flare on the sun's surface. The resulting coronal mass ejection hit Earth roughly 17 hours later, triggering the most powerful geomagnetic storm in recorded history. Telegraph systems across Europe and North America failed. Operators reported sparks, fires, and electric shocks. Some telegraph lines worked without batteries. The induced current in the wires was strong enough to transmit signals on its own. In 1859, the telegraph was the most complex electrical system on the planet. Today, the most complex electrical systems on the planet include power grids, GPS satellites, internet infrastructure, hospital equipment, water treatment plants, and everything that depends on any of those things, which is everything. A 2013 study by Lloyd's of London estimated that a Carrington-class event today could cause between $600 billion and $2.6 trillion in damage to the United States alone. High-voltage transformers, the kind that take years to manufacture, and there are no spares for the Aussie, could overheat and fail across entire regions. The recovery timeline for the worst-case scenario: years, not weeks. In March 1989, a geomagnetic storm roughly 3 times weaker than the Carrington event knocked out power across Quebec for 9 hours and damaged a transformer in New Jersey. That was a moderate event. In July 2012, a Carrington-class coronal mass ejection missed Earth by roughly 9 days of orbital rotation. 9 days. The probability of a Carrington-class storm in any given year is estimated at around 0.7%. Over a century, that's roughly a 12% chance. The budget specifically allocated for protecting the U.S. power grid from geomagnetic storms is not zero, but it's nowhere close to proportional to the risk. Space weather forecasting gives us minutes to hours of warning. What specifically most grid operators would do with that warning is a question that remains largely unanswered. Number 1. Antibiotic resistance. Every other disaster on this list is something that might happen. This one is already happening. In 2019, antimicrobial resistant infections were directly responsible for roughly 1.27 million deaths worldwide, more than HIV, more than malaria. By some estimates, that number could reach 10 million per year by 2050 if trends continue. The mechanism is straightforward. Bacteria evolve. When exposed to antibiotics, the ones that survive pass their resistance to the next generation. We've accelerated this process by using antibiotics in agriculture at industrial scale, prescribing them for viral infections they can't treat, and allowing over-the-counter antibiotic sales in countries where no prescription is required. The result is a growing list of infections that don't respond to first-line drugs. Some don't respond to second-line drugs. A few don't respond to anything we have. MRSA, drug-resistant tuberculosis, carbapenem-resistant enterobacteriaca, the group sometimes called nightmare bacteria because carbapenems are the last resort, and when those fail, there's nothing behind them. The pipeline for new antibiotics is thin. Developing a new antibiotic costs over $1 billion and takes more than a decade. The financial return is low because the goal is to use the drug as little as possible, which is exactly how antibiotics should work and exactly why pharmaceutical companies aren't racing to make them. We are, in practical terms, running out of antibiotics faster than we're making new ones. This isn't a future disaster.
But the shelf fills quickly.
This is a disaster with a body count that increases every year, happening in every hospital in every country. And the primary response has been reports, conferences, and action plans that describe the problem more accurately with each passing year without proportionally increasing the resources to solve it. 5 scenarios. 1 hypothetical wave that probably won't be as bad as the original model predicted. 1 supervolcano that probably isn't going to erupt, but could still do plenty of damage in smaller ways. 1 fault line that will absolutely rupture. The question is when and how bad. 1 solar storm that missed us by 9 days in 2012, and 1 slow-motion crisis that's already killing more people per year than most of the others would in a single event. The pattern across all 5 is the same. We know what will happen. We have models, probabilities, damage estimates, timelines. The science isn't the problem. The problem is that humans don't prepare for things that haven't happened yet. We wait for the earthquake, then we update the building codes. We wait for the grid failure, then we talk about transformer stockpiles. We wait for the infection that doesn't respond to anything, and then we fund the research. Every item on this list has a published prevention cost that is a fraction of the projected damage cost. And for every item on this list, the prevention budget is smaller than the damage estimate by orders of magnitude. We don't have an information problem, we have an action problem. And the action problem is itself a disaster we keep pretending won't happen again. We've been talking about things that can kill you: your brain, your house, predators, planets, caves, experiments. Next week, something different. The most unfair battles in history. Fights where the numbers said it was impossible, and some people won anyway.
Use this knowledge to our advantage in the